So in this video, we're going to talk about the idea of partial pressure, okay? And we can use partial pressure to solve for a multitude of things. In this case, we're going to go for a particular mass, but we're going to go about the idea of how to solve these, okay? And so in this problem, I have a 1 liter mixture of helium, neon, and argon, which has a total pressure of 662 millimeter mercury at 298 Kelvin. The partial pressure of helium is 341 millimeters mercury, and the partial pressure of neon is 112 millimeters mercury. What mass of argon is present inside the flask? So we need to find the mass of argon that is present inside the flask. Well, notice that we actually don't know the actual partial pressure of argon itself, okay? And so in this case, we know that the pressure total is equal to the pressure of helium plus the pressure of neon plus the pressure of argon, okay? So therefore, if we want to solve for the pressure of argon itself, okay, if we want to solve for pressure of argon, then we know that pressure of argon in this, I keep on saying organ, pressure of argon in this case would be the pressure total minus the pressure of helium plus the pressure of neon. Okay, and the idea is that if I have the pressure total, I could just simply subtract these numbers from the total pressure to get the pressure of argon itself. The remaining pressure must be argon. And so if that is the case, then we know the pressure of argon is going to be 662 millimeters of mercury minus 341 millimeters of mercury. Okay. And remember, negative signs are being distributed here, so this is also being subtracted. So the pressure of neon happens to be 112 millimeters of mercury, okay? So we plug this into our calculator, 662 minus 341 minus 112, that is approximately 209 millimeters of mercury. Okay, so that would be the pressure of argon inside the gas, inside the flask, and it's asking for what mass of argon is present inside a flask. Well, hopefully we should know by now that the ideal gas constant is being jumped out at us right now. So that's the formula we got to use. Okay, now my pressure is given in millimeters of mercury. Okay, the idea of PV is equal to nRT does not deal with millimeters of mercury, and it deals with ATM. So I'm going to convert this to ATM. So 209 millimeters of mercury. How do I convert this to ATM? Well, I know that for 1 ATM, I get 760 milliliters of mercury. Okay, so 1 ATM is equal to 760 millimeters of mercury. Okay, so if I want to go to ATM, my millimeters of mercury has to be on the bottom, because those will cancel out being divided. Okay, and then for 1 ATM, okay, so my ATM will be on the top. Notice that these will cancel out to give me only ATM, and so when I divide those two, I should get approximately 0.275 ATM. So this is the pressure. Now we know that PV is equal to nRT. Okay, and look, in order for us to get the mass of argon present, we need to solve for moles first, because if we solve for moles, then we could simply go to grams using the molar mass. And so if that is true, then N, okay, if I divide by RT on both sides, N is going to be approximately PV divided by RT. Okay, and so if I plug everything, well, what's my pressure? Pressure is 0.275 ATM. The volume is 1 liter. Okay, R we know is the gas constant, so this is 0.08206 liters per atmosphere, moles per Kelvin. Okay, and we multiply that by the temperature, which happens to be 298 kelvins. So this is 298 kelvins. Okay, and so when I plug this all into my calculator, 1 times that divided by 1, so that should give me approximately 1.125 times 10 to the negative 2 moles of argon. Okay, Well, now I know the molar mass of argon. So if I take this and say, okay, 1.125 times 10 to the negative 2 moles of argon, if I need to get the mass of it, okay, I know from the periodic table, 1 mole of argon happens to be 39.948 grams of argon. Okay, so this is just the molar mass conversion. And notice that moles on the top, moles on the bottom, moles on the bottom, moles on the top, so moles will cancel out, they only give me grams. And so when I multiply these two, I should get approximately 0.449 grams of argon. Okay, and so this is how we use the idea of partial pressure to solve for any mass. Okay, but the idea is that we should know the general procedure behind solving these types of problems.